and I want to go ahead and introduce him to you. So Dr. Tolley is going to be speaking on design, fabrication, and control of biologically inspired soft robots. He is an associate professor in mechanical and aerospace engineering and director of the Bio-Inspired Robotics and Design Lab at the Jacobs School of Engineering, UC San Diego. Before joining the mechanical engineering faculty at UCSD in the fall of 2014, he was a postdoctoral fellow at the Weiss Institute for Biologically Inspired Engineering, Harvard University. He received the PhD and MS degrees in mechanical engineering with a minor in computer science from Cornell University in 2009 and 2011, respectively. His research seeks inspiration from nature to design robotic systems with the versatility, resilience, and efficiency of biological systems. Example topics include soft robotics, origami robots, systems capable of self-assembly, and his work has definitely appeared in leading academic journals like Science and Nature, and he's actually won the U.S. Office of Naval Research Young Investigator Program Award and a 3M non-tenured faculty award. So without further ado, I'd like to Dr. Tolley to share his screen, and we're excited to hear his talk.
Great, thank you, Michelle. Let me see if I can get the right screen shared here. Okay, hopefully you can see my my presentation there.
Yes, we can. And just a little housekeeping, Dr. Tolley, 1 second, is please hold your questions till the end if you have questions, and please put them in the chat and we'll be sure to get them at the end of Dr. Tolley's talk. Okay, go ahead.
Great, thanks. And yeah, I'll try and leave plenty of time for questions and discussion at the end. Thank you for having me to this fantastic summer school workshop. I think, you know, I'm just waking up here on the West Coast of the US, but it looked like the schedule for today was fantastic, and how I caught the end of the discussion. It's nice to see you. So I'm going to talk about some of the work from my group, as you just heard, on design, fabrication, and control of biologically inspired soft robots. And the general idea that sort of unites my research, or the general theme, is that we look to nature for inspiration into how to improve our automatic systems, our robots, essentially, right? And as just some examples here, I've looked at systems that are inspired by something like the octopus that has a completely soft body. We've looked at taking advantages of new manufacturing approaches that allow us to design in a much broader design space than what we would often see in robotic design, where we can do things like have functionally graded materials. So the picture on the top is the beak of a squid, which is itself rigid but embedded in a soft body, and you have this gradual stiffness gradient connecting the two. And so we've looked at robotic systems that have these similar kinds of functionally graded materials. And then the example on the right here is self-assembly by folding, which is useful in cases where it's relatively easier to make flat things and then fold them up into to access the 3D space. And I think you just heard some more about that. So I know this school is focused on rehab and wearable robotics. We have some projects that touch on that, but I'm going to focus more on the sort of fundamentals of soft robots and how to make them and design them. And I would argue that the assumption of rigidity has, for most of robotics, been central and fundamental, right? And the reason is The things that allow us to sense the world, to sense movement and deformation in robotic systems, are usually expensive. And so the typical approach to robotics, as in the video that you see here, has been to design our robotic systems to be as rigid as possible. What that allows us to do is it allows us to assume that all the motion in a robotic system happens at the joints. You put a sensor at the joints. You can come up with a model where you can predict the motion of that system, and then you can get very high precision and very high accuracy in the control of the end effector position. And if you want to do something like a manufacturing task, like you see here, that's very beneficial. The flip side of that, the downside of that we don't as often hear about, is in order to get that precision and accuracy, you have to, that assumption has to hold. You have to have perfectly rigid bodies. Wherever where you don't have joints, you have to have no deflection. And in the real world, of course, we know that materials deform. If you stress them, if you add forces, they're going to deform. And maybe we don't always want to push to that extreme of being as stiff and rigid as possible, but we want to take advantage of some of the space in between. And in my view, that's essentially what we're talking about when we talk about soft robots, is getting rid of this fundamental assumption. And especially if you're thinking about the kinds of things that this school addresses, or for example, search and rescue in a collapsed building, inspection of a damaged nuclear power plant, or assisting humans with daily tasks, you can potentially, there's a lot of potential upside to thinking about soft, deformable robots. Of course, that approach also presents a lot of challenges. So if you have a body like the octopus here that we see that can deform continuously, has no rigid parts, so it can, squeeze itself through all sorts of small apertures like the one you see here. The downside of that is now you have to sense everywhere, right? You have to, if in order to understand the shape of your body, you have to have sensors all throughout, which is expensive, ton of information. You have to figure out how to synthesize that information to understand the state of the system and in order to control it. So these are very non-trivial challenges that the sort of soft robotics community is now starting to address. And you usually end up, the approach people normally take is they simplify this problem in one way or another. But that, as I said, the potential of this, if you can do that, the potential is you can have a system that is inherently safe for interaction with humans, that can achieve versatile manipulation, and that can have complex environments, interactions with a complex environment, and employ the materials that the robot is made up of in order to simplify those interactions in some way. Okay, so I'm going to give some examples of recent work from my group that has sought to do this, and thinking about questions like how can soft legs simplify walking? How can the control of stiffness be useful? How can a soft body be beneficial for swimming? And thinking about adhesion, sticking to things, and where soft structures can play a role. So I will go through these fairly quickly, and as I say, if you have questions, I will be happy to address them. So this is an image from a review paper that I wrote with Daniela Roos about 6 years ago now. And even then, 6 years ago, there were many people in this sort of soft robotics community thinking about how to move around the world and interact with the world. This is just some examples. Often we're looking to biology for inspiration because that's where the examples of soft bodies are that we see. And so you see here robots inspired by fish, worms, snakes, manta rays, etc. So zooming in on one of those examples, this was some work from my postdoc in 2014, where we looked at, this is with Rob Shepard, Rob Wood, George Whitesides, we looked at can we make a sort of large-scale soft-bodied walker? And the way that we do this is using the most sort of off-the-shelf components we could. We essentially have patterned channels within a soft elastomer body. And when you pressurize these channels, when you inflate them with a strain limiting layer on the bottom of these limbs, you can cause the limbs to bend, right? So it's a very simple concept, and we're just taking advantage of the fact that the pressurized air is going to naturally distribute to achieve a sort of continuous deformation over the body. Of course, it's not always as simple as that. You can even see in these videos some places where you have the Mullins effect with rubber, which means that you get one part of your body that gets a little bit weaker, and now the next time you pressurize it, that's going to be the place that stretches a little bit more, and now it has more exposed area. And so it's a sort of positive feedback where you can have sort of aneurysms. And these are things that we see in biology, right? These are things that we want to avoid in our own, cardiovascular system. And so challenges that nature has solved by, for example, using fiber wrappings around our vessels and pressure vessels in our body to try and minimize, but at some point you're not going to get rid of them completely. But anyways, the point here is that when you address some of these challenges, you can design a soft-bodied walker, and it has some nice advantages, like you can drive over it with a car, and it's going to be able to continue walking. One of the main challenges with this approach from that work was the manufacturing, the fabrication. So we were using molding. We were 3D printing molds. On the lower left here, you see two parts of a 3D printed mold. This is for a different robot with a 3D geometry. But the molding approach presents all sorts of challenges. So either you need complex molds or you're limited to 2.5D structures. In the top left here, you see how we created, in order to limit the amount of rubber that had to stretch for the legs to bend, we added these metal fins into the top of the robot. So there's a lot of sort of creativity and art involved in this kind of molding process, which is a huge challenge. So we started to move towards, rather than 3D printing the molds, we thought about, could we directly 3D print the system? And the advantage of that is we have multi-material 3D printing technology coming online that allows us to do things like not just print flexible or rigid components, but combinations of the two. And we can print them, as I mentioned earlier, in stiffness gradients, where we gradually transition from rigid to flexible, for example. And that's something that you see in nature, because you don't want the stress concentrations that are going to occur when you have a very abrupt transition. So using this Stratasys Object Connect, it's not meant to be an advertisement, but using this one particular printer, we were able to print over sort of 3 to 4 orders of magnitude of modulus. And there are other technologies coming online every day that are bringing us new and improved materials. With this particular printer, one challenge with these materials is they tend to be very viscoelastic. So there's a lot of energy loss in deforming these materials as compared to something like a silicone rubber. So, that's one of the trade-offs there. But as I say, these materials continue to improve. So one thing we were interested in, and this was back when I sort of started at UCSD, is we started thinking about, okay, how can we print an actuator that can bend about 3 axes, essentially? So instead of a single controlled degree of freedom actuator, can we control the bending in 3 planes? And we used a design that had been previously proposed by Suzumori and others, which is essentially 3 tubes. And if you extend one of the tubes, you're going to bend in the opposite direction if it's attached to the other 2. So what we end up with is this sort of module that can bend in space. And also, if you pressurize all 3 tubes, it can also extend, actually. So the nice thing with once we start 3D printing these things is we're not bound to simple geometries. So we can get over the fact that the material we're printing with has a limited sort of strain to failure as compared to something like a silicone rubber using these bellowed designs. So something that can essentially unfold instead of only stretching, essentially. So this was the design that we came up with. This is a little video showing the use, the control of one of these modules to, in this case, just as an example, control the direction this laser pointer is pointing on the screen, okay? And so that process is fairly repeatable. In this case, we were using feedback control on the pressure in the 3 chambers that we're controlling with these stepper motors, as you can see here, not on the position of the laser. So we could do better if we did visual servoing there. But we showed that you can, use this module for various things like manipulation, and we were interested in essentially making a new version of the walking robot that could now, because you have these, you can bend in space. Essentially, you have 3 degrees of freedom per leg. You actually have more control over the legs. You can walk over more varied terrain. So that was the next step here. We presented this at ICRA in 2017, where in this case, we have tethers coming off the robot. So we have a pump and valves and microcontroller and all this off board in this case. But we wanted to look at, if you have these soft legs, you can get over rougher terrain like pebbles, etc. How can these soft legs be beneficial? And so the sort of hypothesis here was we could come up with a simple gate, and it would allow us to make reasonable sort of progress on different terrain, and that we found to be true. And this is one example from the let me see, I don't know if you guys are seeing my mouse right here, but you can see the speed of the robot on different terrain. So, so this is great. There's a couple challenges, obviously, still to address, a number of challenges still to address. And one of them is I challenged my student Dylan, who, by the way, just graduated, to think more about how can we make an untethered version of this system. Ideally, we want something that can operate out in the wild, and we don't want to have to carry around all the electronics, etc., off board. And we were inspired by some work that came out of the Whitesides lab after I left Harvard, which was looking at these pneumatic valves with a little bistable membrane on the inside. And essentially, these valves can act like an inverter element. So if you put 3 of these valves together, you get a very simple circuit, pneumatic circuit in this case, that propagates a pressure state through the circuit. And basically, the way it works is if you hook up the circuit in this way, where each valve is acting on the other side of the next valve. Once you pressurize one valve, it essentially pressurizes the previous valve in order to flip its state, in order to invert its state. And so these little valves, they have membrane. When they're deflected in one way, it kinks the tube on the top, and when they're deflected the other way, it kinks the tube on the bottom. That's basically the idea here. And so you can get a negative sort of feedback. And if you look at the pressure in each of these 3 valves of this ring oscillator circuit, you get this sort of state where it increases in pressure and then decreases. All of this the entire circuit is just pressurized. You have P supply here that's connected to the bottom of each valve, and then you have P atmosphere. So just like in an electrical circuit, you have high voltage, low voltage. You have the same thing here. You apply constant high pressure to all of these valves, and just by virtue of the way they're connected, they're going to get a constant oscillation or propagation of pressure state through the system. Now, if you connect up your actuators on this diagram are labeled as PA, PC, PB, PC to the right points in the circuit. Now your actuators are going to start pressurizing periodically, rhythmically, right? So this is great because this is essentially what we see in biological systems. When we go out and walk, we have what's called a central pattern generator neural circuit that generates sort of a rhythmic output. And then that gives us our basic rhythmic motion, and then we use higher processing response from sensors, etc., to adapt that rhythmic motion to respond to obstacles or things like that. So we used this approach essentially to rhythmically pressurize the actuators in a soft-legged robot. The robot you see here in this video, it's not 3D printed, or the legs are not 3D printed. We started using off-the-shelf bellowed tubes, essentially, that we've connected in a similar design to what you saw previously. And the diagonal pairs of legs of this robot are connected together, so they're moving together. Even though only one leg is lifting off the ground, that's just because of the way the sort of where the gravity vector falls. But essentially we have two legs moving together and then the other two legs moving together and propagating pressure states through this through the chambers of the legs. Now you might notice that it looks a little bit clumsy, and that's because essentially we have connected both pairs of legs to the same oscillator circuit. So if you look at the lower right here, we have one oscillator circuit in this video, 3 valves, and that means that the phase offset between the pairs of legs cannot be 180 degrees, which is what we want. It can only be 120 or 240 degrees. Okay, so that's a detail, and if you look at this paper, which appeared this year in Science Robotics, you can see some of those details, but we looked at how to optimize the phase offset between the pairs of legs. But essentially, once you have your basic oscillator circuit, you can control the locomotion of the robot. And then we started to look at how you can tweak this circuit with as simple a pneumatic system as possible in order to, for example, reverse the direction of locomotion. And what we came up with was with one element, which essentially looks like a 4-2 valve, meaning 4 ports connected to 2 ports. If you can see my hands there, 4 ports connected to 2 ports, and you can switch the connections between the two. We can put that into our system right here in order to essentially reverse the direction of motion of the legs. And here you see, actual measurements from the system as we do this, where we're going blue, red, green, and then we reverse the direction. All of a sudden, we're going blue, green, red. And so what that allows us to do is actually, I'll come back to this video in a second. What that allows us to do, if we flip the direction of locomotion, is you can be walking one direction. Here you see these 2 legs moving in one orientation, and then flip to be walking in the other direction. Now, how we're flipping in this case is we have a little soft sensor at the end of this boom. When it hits the wall, it changes the state of a valve, another valve in the circuit. So now we need at least 4 valves to make this robot walk. And if we add 4 of these 4-2 bistable soft valves, now we can control walking in any direction. So here we're changing the state of these 4 valves, S1, S2, S3, S4. We're changing them manually. So we have like a little tethered pneumatic remote controller for this robot. But again, the only thing powering this system is a constant pressure source. That's this tube you see going off to the left. Otherwise, it's purely controlled by pneumatic brain. So we see some potential applications here where you don't need any electronics on board the system. And in terms of thinking about sort of surgical applications, there may be cases like in an MRI machine where not having electronics is advantageous. Or we argue in sort of a mine shaft, some case where you don't want electronics that could potentially cause a spark. then this kind of pneumatic brain might be useful. Okay. So another challenge we thought about here is, well, my original idea was if we can have soft legs, immediately that solves all our problems, right? So we can get something that can, for example, walk on sand, and it's going to be no problem. As some of you may be wondering right now, well, what's going to happen when we put this thing in sand? This is a very simple experiment, but I think it sort of gets the idea across here, which is just because you have soft legs, it doesn't necessarily solve all your problems. Rather than being a good walker on sand, this robot was more of a good digger. And even in the previous orientation you saw where the legs are pointing down, we didn't get the sort of performance we were hoping for in sand. And so that started to motivate us to think about how robots interact with more complex terrain, like what we call granular media or sand. There's a little bit of motion here, but not what we were hoping for. So that's where we started to think about control of stiffness. And the first project here was inspired by some granular jamming work that actually came from the lab where I did my PhD in Cornell in 2012. And the basic idea here is very simple. It's you have coffee grounds in an elastic membrane. If you pull a vacuum in that elastic membrane, all of a sudden the grounds jam together, just like if you have vacuum packed ground coffee in the fridge, you know, it's like a rock. And this can be used to make you know, a very versatile jamming gripper, as you see in this video. So our idea here was, well, if we can now control the stiffness of part of our robot, let's say the feet, maybe we can get improved interactions with a complex ground like sand or leaf litter or some other complex terrain, and do something like change our feet to be soft when we land on the ground so they can conform to rocks, pebbles, whatever it is, and then make the feet rigid when we want to push off. That was the basic hypothesis here. So we took this off-the-shelf hexapod robot, we added little pumps on top, and at the end on the feet, we have essentially little jamming feet. So, you know, elastic membranes with coffee grounds inside. There's some details here because what happens is most of the force that we want to get when we're pushing off is a shear force, and these jamming grippers are not particularly, you know, stiff to shear. They tend to essentially shear relatively easily. So we added in some stiffening structures to the feet, some fibers or little pillars here to increase the resistance to shear. And again, this was published last year in RoboSoft, so please take a look if you want to know the details. But I'll just give you the sort of brief summary here, which is if we take this robot with jamming feet and we put it on different types of terrain, like here you see wood chips, we have loose rocks, and we tested flat ground. And what we found, if you look at this video here on the top, I think it was, so we're walking up a 70-degree slope, and we have rigid or sort of the stock feet on the top versus active granular on the bottom. And what you'll see is that the jammed feet allow the robot to move more quickly than the stock feet, basically. And if you look at the data on the right here, so the active granular is the orange. We actually found on flat ground, we had rigid stock feet, we had active granular, and the green here is passive granular, meaning we're not actively pulling a vacuum, we just allow the weight of the robot to jam the feet. And interestingly, we found that on flat ground, that was actually better than active granular. So maybe it has to do with the timing, or I'm not quite sure what the reason is there, but we actually had better performance with just the passive granular. Whereas on loose rock and wood chips, we got better speed overall with the active jamming of the feet. Okay, so this is one way that you can achieve jamming, but you can think about other ways to have a similar effect. As I say, the basic granular jamming on the left here is you have these particles within elastic membrane. The failure mode or the weakness is if you have a granular jammed beam and now you apply bending load, at some point the grains come apart, right? And they have, and they're not, they can't really resist that motion. They can resist compression well, but not tension. And so the top of this beam is in tension, which means the only thing that can resist that is the elastic membrane itself, which by definition should be very soft. So I'd argue that granular jamming is not particularly good in bending, but there are other jamming approaches people have thought of to deal with changing bending stiffness. And one way that we do this is if you have a bunch of sheets of material that are relatively have a high coefficient of friction, so let's say like sandpaper, and you stack them up inside a membrane, and now you bend that. It's, you know, can be relatively easy to bend, but if you jam it together with pressure, or people have used other sort of electrostatic forces, other approaches, then it becomes much harder to bend. It's like changing the thickness. Now instead of bending many thin beams, you're bending one thick beam, which is much stiffer. Similarly, that allows control of the stiffness in one direction, but if you actually want to change the stiffness in multiple directions, you can use fiber jamming, which is essentially you have abrasive cords or cords with a coefficient of high coefficient of friction, and you jam them together in a membrane. So this is that example of layer jamming, and this is actually some sort of unpublished work, but just some experiments with different materials with different coefficients of friction. And in this work, which we published in Soft Robotics, it's available online. We looked at how we can model this, essentially the stiffness curve that you would expect when you jam layers or fibers together, which fibers, when you look from the side, can look like layers. Essentially, you know that the shear stress, the transverse shear stress, is going to be highest in the middle. So when you have these layers stuck together, if you keep adding load and keep adding load, at some point they're going to start sliding, and you know where they're going to start sliding because it's the high transverse shear stress is in the middle. And so you can start to predict what the shape of this force deflection curve looks like. And of course, when you do this in experiment, like the data you see on the right, it's not as multilinear as you see on the one on the left, because you have sort of the realities of the real world. That means that the whole layer doesn't sort of have the exact same coefficient of friction, etc. But you can sort of predict how these things are going to fail. And so one of the things that we've looked at that maybe is more relevant to this school is actually to make surgical manipulators, and or rather I should say variable stiffness deflection devices. And so this is a very simple device we've worked on, where we have jamming layers within parts of this device. And I'll say, actually, before I play this, if you get squeamish around videos of the inside of pig bodies, you might want to look away for a minute. But this is an example video of using this type of device in minimally invasive surgery, where we want to fold up this variable stiffness device, put it through a trocar, which is the hole that you make in a body to introduce your surgical equipment for minimally invasive surgery. And now we have this relatively flexible device, unjammed, so no negative pressure applied. If we pull a vacuum, it jams and it's relatively stiffer, right? And then we can unjam it again. And so this is a video from testing in a pig. And we want to show how you can use this kind of jamming device to, for example, hold the liver out of the way when you perform an operation on the stomach. So this is a challenge in surgery because the liver is always in the way. And typically, if you want to perform this kind of operation, you need another doctor to sit there with a metal retractor and hold the liver. And then you have to coordinate between two doctors. Oh, you're not holding it in quite the right way. Please hold it higher, move it more this way, in order for the physician performing the surgery to get a good view of what they're doing, right? So you have now a camera coming through one port, surgical devices coming through other ports. And with this device, the idea is you can put it in, the surgeon can manipulate, move it into the right position to hold the liver, and then you can perform the operation underneath. I believe in this case, it's a gastric bypass surgery. And then ideally, we want this device at the end of the procedure, you can, again, unjam it and sort of pull it out of the body relatively easily. Okay, so this is the idea and something we have a company working on commercializing. Okay, so that's layer jamming. As I mentioned, we can do something like fiber jamming. And in this paper, we talked about one potential application. So on the top right, you see that you could make a tool with fiber jamming. In the lower right, we looked at using this as a haptic device. So if you want a glove, excuse me, that you can jam, it provides force feedback. It feels like it provides resistance essentially to give the illusion of holding on to an object. And now if you now make the actuator atmospheric pressure, essentially, you remove the vacuum from these jamming actuators that are along the fingers of this glove. Now your fingers can move more freely, so it appears that the balloon that you were holding in this example has popped. Okay, so this is one example, and that my student Sarab is an expert at making these sort of VR applications like the one you see here. Okay, let's see how we're doing. So it's 7:40 my time, so I think that's maybe 4:40 your time. Let me talk quickly about a couple other projects. So we've thought about swimming. As Michelle mentioned at the beginning, we have some support from the Navy in the US, and they're excited about fundamental research in soft-bodied swimming. And so we've looked at jet propulsion inspired by cephalopods, and there's some interesting prior work here. But if you look at some of the keys for how squids swim, they take advantage of the added mass effect, which is essentially the amount of water they have to carry along with the robot. And what they do is they fill their body with water, and then they force it out a jet, right? When they're filling, they want sort of relatively more resistance to motion, because when you're filling your body, that will tend to give you a negative propulsion. If you're filling your body and water's coming in this way, it's going to pull your body back. And now you squeeze the water out and it gives you positive propulsion. So the ideal case is you essentially look like fatter when you're inflating and thinner when you're jetting. In other words, you want to carry less water along with you when you're trying to go forward, and you can carry more water along with you when you're not. And so as you get the added mass decreases as you're jetting, that adds an acceleration term essentially. So there's prior work by Weymouth et al. Who looked at a sort of example experiment that achieves this, where in this case they essentially have inflated an elastic membrane around a skeleton, and you see that you can get a very rapid motion. But here, obviously, it's a one-shot motion. They've since published, I believe they've recently had a paper looking at a cyclic motion. And this is work from Cecilia Lashke's group, that looked at essentially repeatable motion of squid-like propulsion, where you see the very nice vortex jet that's coming out of the robot here. Although we would argue that the change in the cross-sectional area of this robot is relatively small compared to the squid, so that there's more opportunity here to take advantage of this added mass effect. So the robot that we designed to do this looks like this basic design that you see here. Is very simple, and there's also still opportunities for optimization here. But we wanted to look at something where we have a soft body that is becoming fatter and thinner, essentially. And here we have a very simple actuator, which is just a little electric motor with a decimated rack and pinion actuator. And so essentially, as the motor turns, when these teeth are engaged, the robot compresses. And then at some point, there's no more teeth on the little pinion here, and it slips. And so you can get this sort of rapid jetting motion. On the right, you see an actual video of the robot on a you know, it's on a stationary platform here, and we're doing force sensing. And so we looked at both force sensing, we looked at dye visualization to optimize, for example, the diameter of the nozzle, which it turns out is very important. If you ask the fluid dynamicists, you want to get all of your fluid that you're pumping out of the robot wrapped into one vortex, like the video you see on the right here, as opposed to multiple, which is what you get if your nozzle is too small, like you see on the left or in the middle. You know, nature, if you look in nature, you see that squids, and if you look at the fluid dynamics, actually, you see that the ideal for a squid starting at rest is a ratio of 4 to 1 here. So if you look at essentially the stroke ratio, you want your nozzle to be closer to the size on the right than to the sizes on the left. I think I have another plot that shows that in a moment. But essentially what we quantified here was the different force over time for these different nozzle sizes. And yeah, this is just some still frames from that. So this is the stroke ratio plot I was just talking about. So if we look at the average swimming speed here, now we have an untethered version of that robot where we have the battery and the camera and stuff at the front of the robot here. We find that our stroke ratio, consistent with previous fluid dynamics analysis, is ideal for stroke ratio of about 4. We get the maximum speed. If you go higher or lower, you tend to be less efficient. So anyways, these are the kinds of things that will guide the design of this kind of squid-like robot. But for us, we're very happy to be able to make something, show that we can steer it. Here, we're not doing active steering. We're just adding on a nozzle pointing in one direction, showing that in principle, we could steer the robot. And fortunately, at UC San Diego, we have collaborators. This is at the Birch Aquarium. We have collaborators at the Scripps Institution for Oceanography, with whom we're able to test these robots in a more sort of realistic environment here. You see one of the divers that was helping us with this experiment at the end of the video. This is actually in a tank, in an aquarium tank, but swimming with real fish. And so we argue that this, has the potential to make a robot that isn't going to disturb the fish, is not likely to harm them, but can be used to monitor wildlife. And potential advantages of not getting stuck amongst kelp and in rocks, etc. Okay. So now I'll move on to the last topic for me for today, which is adhesion. And there's a couple projects that we've had recently looking at bio-inspired. Well, one's bio-inspired, the other one not so much, but 2 approaches to adhesion. The bio-inspired one, for this work, we looked at the clingfish, which is this little animal here you see in this animation from previous work that even when euthanized, is able to stick to something that's rough and slimy like a rock, okay? And so you see this euthanized fish attached to a 6-pound rock purely based on pressure, like a suction cup. So if you look at the animal, essentially it has this these modified pelvic fins, and it generates this little suction disc between the fins and structures on its body. where you can actually zoom in and look at these microstructures. What you have is you have these sort of roughly hexagonal raised structures around the lip of this suction disc that allow the fish to conform to a rough surface and also allow fluid to channel out of the way so that you get very nice intimate contact with something rough like a rock, which allows you to hold a negative pressure in the center of this suction disc. Okay, and we have some work looking at, this is my student Jess Sandoval, who has looked at this from both the biological side as well as the engineering side in order to understand what these fish do and how we can replicate. And if I were to sort of give you a model of some of the things going on in the fish, you want a relatively stiff backing to this suction disc. You want these microstructures with fluid, with features for channeling fluid around the outside. You have secretions to help in sealing and these soft extrusions to make this intimate contact. Now, the first sort of bio-inspired suction discs that we made were much simpler, where essentially we have, instead of one stiffness, which is what you would normally have in a commercial suction cup that you might use in your bathroom or whatever, the simplest thing that we can do is essentially have a relatively stiff disc with a relatively soft membrane. And the sort of first hypothesis here was, would that improve our adhesion on rough surfaces? So essentially approximating all of these microstructures, et cetera, as a soft layer. And then we started to look at other things like, what if we have different sort of slits kind of representing what the fish has, and what if we add microstructures, et cetera. What we found with that first question was, sure enough, just by patterning different stiffnesses of the disc in the right places, we were able to stick to things, rough surfaces underwater. So this is our artificial suction disc, which it's all colored white here, so you can't really see the different layers, but essentially we have a relatively rigid and soft layer. And we tested out these different sorts of features. If you look at the blue line here, which is the disc that had the best performance, now we're going to look at the stress versus grain size, meaning the roughness of the surface. If you're on a perfectly flat surface like glass or tile, your commercial suction cup, which is the red one here, has the best performance. So we're not beating commercial suction cups on glass. But neither is the clingfish. The clingfish is the green ones here. So they're not as good as commercial suction cups on a perfectly flat surface. As you start to increase the roughness, now you see the clingfish actually does better on rougher surfaces, according to previous work. Our suction cup, our best suction disc, also performs relatively well. We have about half the sort of performance of the biological clingfish on a grain size of 68 microns. And even as we go up to 269 microns, we have relatively good performance as compared to a commercial suction cup. Okay, so just a little bit of patterning of the stiffness and looking at structure inspired by the clingfish, we got a significant improvement on rough surfaces. And the same is true in air, although really our emphasis was getting something that would work underwater. So for this work, we got something that could stick to an array of surfaces. And I should say, I'm not going to talk about it more here, but Jess has since been looking more at some of these other interesting features, as I say, like fluid channeling, microstructures to achieve fluid channeling and more intimate contact. And so we hope to be able to tell you more about that soon. The last thing I'm going to talk about here is another adhesion approach, which is, as I say, not really bio-inspired, but it's a very interesting concept. And so it turns out, if you take a thin membrane and you add a little bit of vibration, like you would get from a pager motor, from a vibration motor that you have in your phone, or like an eccentric rotating mass, for example, and you turn on vibration on right here, and you put this disc in close contact with a relatively smooth surface, you generate adhesion. And let me see, I see there's something in the chat here. Okay, I'll come back to that question in a second. So just to wrap this up, so we don't run out of time, the interesting thing that happens is you generate a low pressure region essentially underneath this disc. You essentially get the fluid under the disc to move by vibrating this disc, which generates a low pressure. And the interesting thing is it's controllable when you turn the adhesion, when you turn the vibration on. You get adhesion like this 14-gram disc supporting 500 grams, half a kilogram. And you, but the most interesting thing, as illustrated by this video, is you get adhesion, normal adhesion without shear adhesion. So normally, if you use gecko adhesive or glue or electro adhesive, if you're stuck this way, you're going to be stuck this way. And if you want to be a mobile robot, that's not good, because now you need to move. If you're sticking to a surface, you now need to peel off, reposition, put somewhere else that requires multiple legs, multiple adhesion pads, etc. But if all you want to do is move across a smooth surface, it's kind of nice to have an adhesion mode that sticks only in the normal direction. So we did some quantification of the effect of frequency and the size of the disc. There's an optimum for both of these for our particular design here. It turns out if you look at the sort of, we put some pressure ports underneath the disc here and looked at where the negative pressure is being generated, and it's all right in the middle of the disc. So if you actually look at the shear, the normal stress, it's larger the smaller the disc is, but if you look at the overall force, there's going to be some optimum. So increasing the radius of the disc does add some more adhesive strength up to some point, essentially. This is that point that I made earlier, which is if you look at our vibration adhesion here, it's all in the normal direction, or all in the tangential direction rather, and no force in the normal direction. And what we essentially did to make a mobile robot that takes advantage of this is we added some wheels with a little spring in between. So we get this disc that sticks to a surface, and then we get some preload. The spring provides some preload on wheels that allow us to now drive around the surface. So in the top left here, you can see driving up a wall. You can drive on a relatively curved surface because it's a flexible disc, and you can do something like pick up a soda can and drive around with it. Now, one major caveat is that this is vibrating at audible frequencies. So, our original idea was maybe we can use this in the home. It's going to be really annoying, so you'd really have to think about how to, make this thing quieter if you wanted to do that. But we think it's an interesting controllable adhesion mechanism. So I'm going to leave it there. Let me just say before I wrap up that we have a number of collaborators on various projects I've talked about today. Of course, I have to acknowledge our funding sources, NSF, 3M, ONR, BASF on different projects. And most importantly, I want to acknowledge the group of students that is helping me, that is really doing all of this work. And I'm helping them, I should say. And also you see Professor Young-Lei Park, who was visiting our lab last year. Okay, so I'm going to leave it there, and very happy to take any questions we have time for.
Thank you so much for that presentation. We do have a few minutes. I know that right after this is workshop, so if people have a lot of questions, we can stick around and pick Dr. Tolley's mind before we move into the workshops. So there is a question in the chat from Miranda. Miranda, do you want to unhook your mic and ask your question, or do you want us to just go ahead and answer?
No, it's okay. I can ask Michelle, but thank you for offering. Yeah, so I have a couple of questions. Sorry about that. My first one is about the fiber jamming. I was just wondering about how the fibers are arranged. Is it in like a weaving pattern, or are they kind of all arranged in one direction?
Yeah, great question, Miranda. Thank you. And by the way, if you're able to turn on your camera, that's great. Don't feel like you have to, but it's always nice to see
Oh,
people.
okay.
Hi, great.
Hi.
Yeah, thank you for the question. So our fibers in the fiber jamming actuator, we thought a lot about this. We ended up putting them, they're basically just in a straight orientation. We thought about, do we want to fix them to the ends, right? And so there's other fiber jamming work, very nice fiber jamming work, which had half the fibers attached to one end, half the fibers attached to the other end. In ours, we ended up, the examples that I showed, I think they were free floating, but we had actually tested both cases and didn't notice a huge effect. In terms of weaving, we definitely didn't try to weave them in sort of braids or something like that, but I think that's a really interesting idea. And maybe now there has been other work that's look at woven jammed fibers. But I think at the end of the day, if you want your stiffness to be sort of equivalent in all bending directions, probably a good place to start anyways is sort of straight fibers, and that seemed to work for us.
Okay, thank you. And then one other question I had was about how much research has been done into portable granular jamming actuators, and if there's been any done into irreversible granular jamming. So say a certain portion of the actuator can become irreversibly changed in stiffness.
Huh. Yeah, I think that's a really interesting idea. I mean, that's what you're sort of describing there is cement, right? So cement is basically you take a bunch of grains of random sizes, stick them together, and irreversibly jam them. Now, so for reversible, so I think to answer that, I think you could certainly imagine other ways to do that, where you have some sort of epoxy that you infuse in, and you create sort of irreversibly strong structures. I haven't seen anything, I don't know anything off the top of my head that does that in a very sort of portable way, but I think that could potentially be done. In terms of portable granular jamming reversible, it can certainly be done. So I mentioned some work from the lab at Cornell where I did my PhD. John Amond was the lead author on that. He ended up starting a company called Empire Robotics, and they made these universal grippers as a product for a while. They're now defunct, they've closed, but there may be other companies that have picked up that technology. And I know that at one point he had an example with just a little, tiny, basically he used a pump that you use in a pressure cuff to sense blood pressure and a little battery. And so it can be certainly very portable to make something that can jam like that.
Okay, fantastic. Thank you.
Thank you, Miranda. So Camilo, do you want to unmute your mic and ask your question about surgery applications?
Okay, thank you. I've got no camera. Mine is broken, so sorry. I can show you. I can show you my video. And Dr. Tolley, I was thinking about the surgical application you talked about, and you showed us the mechanism using fiber jamming, and I was wondering, is it possible to use this mechanism for achieving bending of a surgical manipulator? And my main question is, do you think there is room for further miniaturization in with this kind of application?
Yeah, so I think the question was, Camilo, for fiber jamming, can we use it for surgical applications, and can we miniaturize it more, basically, right?
Yeah, it's this.
So we haven't used it for surgical applications. The surgical application I showed was with layer jamming, but in principle, I agree that you could use fiber jamming to make something that's, again, transitions from relatively soft to relatively stiff, where that could be useful. I don't know exactly where that is, but I'm sure there's plenty of applications. In terms of miniaturization, I think it's certainly possible. So one challenge is coming up with fibers with a relatively high coefficient of friction. It turns out your jamming ratio is going to be a function of your coefficient of friction. So what we used was off-the-shelf abrasive fibers that you would use for some manufacturing process. But I'm sure if you talk to materials people, they could tell you about clever ways for making high friction, nanofibers or microscale fibers, and that could work. But I don't know off the top of my head what those fibers would be.
Okay, thank you so much for answer.
A final question from Dr. Su. Do you want to on mic and
actually? I had the question also. It was on top, but maybe later. Okay, no problem.
Here, go ahead. Sorry, and then we'll go to Dr. Su.
Yeah, thank you for the impressive talk. Really a lot of cool projects. So to your adhesion actuator, what are the key metrics, and also how those actuators from your lab could be maybe different from the Gecko adhesion actuator?
Thank you, Hao. So I think you're asking for the two. We talked about two adhesion projects. What are, how do we quantify their performance, and how do we compare them to other alternative adhesion approaches like Gecko adhesion? Is that what you said?
Yeah. Just in general, because there are many solutions.
Yeah, absolutely. Yeah, so I would say, how do you quantify? First of all, I would look at adhesive stress, right? So at some point, it's not just the stress that matters. So that would be the force divided by the area, of course, but it may be true that some kinds of adhesion work better at smaller or larger scales, right? So for a robotic system, obviously you care about the overall force, but the easiest way to compare is adhesive stress. And yeah, I don't have the numbers off the top of my head, but I think both of these approaches are relatively competitive in terms of stress, but that's not where I see, I think the real unique things we were going after for the first one was being able to stick to rough surfaces underwater, which is kind of tough. And so a lot of these approaches like Gecko adhesives don't work very well underwater because they're relying on van der Waals forces that you just don't get that kind of intimate contact if you have fluid in the way, essentially. So that's, I think that's with the Clingfish inspired adhesion, that was one focus. Now for the vibration-based adhesion, the real benefit, I think, compared to something like Gecko adhesives is what I was talking about with, you want to stick normally without a resistance to shear motion. And so there's not a lot of things that do that. I mean, if you have a suction cup on a lubricated flat surface, sometimes you can slide it around, right? So that can work, but it's not as easily controllable. You can't just, press a button and it disengages. So having something that you can turn on, turn off, and can move along a dry surface is, there's not a lot of other examples. So I think that's the advantage there.
Wow, that's a really unique, impressive solution. Yeah, thank you.
Yeah, thank you. And I should say, after we published this, we came across, someone pointed out some patent where there is another group who's done something kind of similar too. So we're looking at that and seeing if how what we did compares to theirs.
Yeah, thank you. Yeah.
So there were two questions in the chat that I missed. Amir, if you want to unmute your mic and ask your question, and then we'll take Elena, and then we'll wrap up this session and move to the workshop. Go ahead.
Sure. First of all, thank you very much for this quite interesting presentation. My question was related to the pneumatically actuated quadruped robots that you presented. As far as I know, the main problem for these kind of systems is the position error in the task space. What was the position error, let's say, that you faced with? I was wondering about.
Yeah, that's a great question, Amir. And I'm sorry, I don't know the number off the top of my head, but certainly for this actuator, certainly on the order of millimeters, and it's not a big actuator, so it's a fairly big positional error. But I think that the main point there is you're probably looking to use a soft manipulator in cases where the positional error is not the only metric of concern. right? So if I would argue if the main metric you care about is positional error, you probably want to go with a rigid solution, because that's, as I started off saying, that's kind of where you're going to get your best precision. If your metric is, how much force do you apply to something that you interact with, let's say something that you can't sense with cameras or something like that, then I think that's where your soft robot, your soft actuator is going to shine. So yeah, so I guess I'm trying to dodge the question, because I don't think it's the right metric for a soft actuator, but you can find that metric, and you can improve it. But the things that you would do to improve positional error for a soft robot rather, usually look like making it more rigid, right? Higher pressure, stiffer structure, and then it's kind of like, well, why make it soft in the first place?
Yeah, also just one more thing for this surgical operation that you show the inflatable structure, also to, let's say, increase the view of the doctors during the operation. Also in that case, I think to, let's say, to locate it in a proper way inside the human body. Also in that case, what I understood from the video is that could be a challenge to control in a correct way, or did you face with that kind of problems? Or
yeah, absolutely. That device is manipulated by the surgeon, right? So they have kind of rigid grippers that they're putting in through the ports, and they're moving it around by hand. So if you wanted to automate that process, you're absolutely right. That would be a huge challenge. You'd have to figure out how to actuate all those degrees of freedom, or have some other system that's moving it, right?
Thank you very much. That's it from my side.
No, great questions, Amir. Thank you, and
thank you.
Lots of challenges there.
We have about three additional questions in the chat, but I wanted to check in with Mateo about timing. Is it okay to have Dr. Tolley continue to answer these questions, or do we have a kind of a time where we need to switch over?
I would say that, hello everyone. I would say that if Professor Michael Tolley is still available for, I would say, another 5 minutes, we can proceed, and then we can start with our team working session. So if Professor Michael Tolley is available, I think it will be quite a good thing to just try to answer the last couple of questions.
Yeah, I'm going to summarize 2 of the questions that I saw, and then maybe we can. There was a question about working on the first robot that you showed that was moving quite slowly. There was a question about improving the speed, and then there was another question related to that same robot about the approach to modeling its kinematics. So if you can maybe combine the answer to those 2 questions together, and then we'll deal with the other questions.
Sure, yeah. So in terms of speed for pressure driven soft robots, you're going to be limited by the fact that you have to move air into these actuators. So how can you improve that? Well, you can make actuators that essentially require less air to inflate. But that's also going to limit your force. So there's certainly, if you have a certain pressure, it's acting over a certain area, that determines the amount of force that you're going to get roughly for the actuator. So there has been previous work, for example, on soft actuators that move quickly from the Whitesides group. And what that essentially, the way that they achieve soft actuators that move more quickly is with a more complex, convoluted design where you have this pressure mostly acting in the direction that you want it to act. And so there are tricks that you can play, but there's almost always trade-offs. I think, so we have some other work underway that I hope to be able to talk about soon, where we've looked at how to achieve relatively quick motions with relatively slow actuators for soft robots. But we did previous work where we use combustion. So that's one way to very rapidly generate high pressures. And that's something that we use today in internal combustion engines. So I think there are clever ways to make pressure-driven soft robots faster, but there are some, sort of fundamental limitations there. So that's kind of a high-level answer. And then in terms of the kinematics, you know, we for our for the soft-legged robots that I showed used the same kinds of assumptions that a lot of people use in soft robotics, which are like constant curvature assumptions. So if you have a pressurized, if you have a continuous bending actuator and you can assume the curvature is constant along that actuator, then you can do the forward kinematics, predict the position of the end effector that way. Obviously, well, I would argue that if you really want to make a soft robot, it's probably because you don't want it to have a constant curvature, right? You want it to be able to interact with things and assume complex shapes like that of the octopus. And then at that point, if you really want to predict kinematics that way, I think you need something more like finite element analysis. I don't see, you know, I don't see some really low order model predicting those kinds of interactions. You can potentially get away with a reduced order model, but I think you're going to need more computational power to really predict the forward kinematics in those kinds of cases. So I hope that sort of answers the question. Please let me know if it doesn't.
Okay, we'll take one last question that's in the chat. It's from Raul. Raul, do you want to unmute and ask quickly that question?
Yes, thank you for your talk. My question is more regarding about like manufacturing process. I saw like you mentioned about like 3D additive manufacturing, 3D printing. So like I saw also like you use kind of a Stratasys printer. So my question is more like what type of printing process did you use for clean all the cavities in the robots? Because it's like a pneumatic actuation. So I know like Stratasys have like kind of a ultrasonic cleaner also, but sometimes like that kind of material can cause like some damage in the material. So
yeah.
Basically it's like.
Yeah, thank you, Raul. So you're bang on, and so if you use something like the Object Stratasys system, removing support material is a huge challenge, and even like they have, you know, newer material, support material that's supposed to be dissolvable, and as you say, sonication, etc. Even with all of these things, we've always found it to be a huge challenge. For those robots that I showed where we're 3D printing these complex geometries, it's essentially a lot of work and you need some clever design. So for example, these bellowed actuators, what my student Dylan actually ended up doing was he had openings at both ends. And so you can shoot water through or use mechanical scraping to remove some of the support material. And even then you do that, you spend a lot of time doing that and you never quite get everything, right? So that's going to affect your material properties or your sort of the properties of the final print. So I think that's a challenge that we haven't really come up with a sort of cure-all solution for. I think the way that we're gonna probably go as a community, broadly is I think there's printing methods that don't require that kind of support material. So if you look at like the carbon 3D, where you're essentially printing by curing, photo curing still, but in a sort of vat of goo, and you gradually raise your part out of this vat of goo, and you're curing on the bottom, you can potentially get something that way that doesn't require support on the inside. But my understanding, we haven't used the carbon 3D directly. My understanding is that making sealed devices is still somewhat a challenge with that approach. The other thing that we're working on, and again, this is something we haven't published yet, but we do have some funding from BASF, and we're looking at ways to make pneumatic actuators using FDM, fused deposition modeling or filament printing. And so I think it's possible. There's also some sort of support challenges and sealing challenges, but I think we should have more to say about that soon. But generally, I think you're going to see different printing approaches that are really tuned for different kinds of devices. And so, but you're absolutely bang on that the Stratasys support material is a challenge.
Well, we need to wrap this up. Thank you so much, Michael. This is a awesome talk. Very, very informative. The students need to move into workshops where they're going to begin to kind of maybe debrief with each other about what they've learned today. And does Stefano or Matteo want to talk about what happens in the workshop so that we can prepare the students for transitioning?
Let me just say thanks again, and
thank you, Dr. Tolley. Appreciate your time. And I'm going to assume that if students have questions or further questions, they could contact you via email.
I'll put my email in chat here.
Okay, perfect. Thank you.